Okay, ich glaube, ich fange einfach mal an. Ne? I decided to give this presentation in English because, well, I would be able to reach a wider audience. Welcome to my presentation about the data structures in magnetic scrolls text adventures. And yeah, you may ask yourself, why am I talking about those? Well, it is actually because of this article here. Question to the room, does anybody know this article? You know the author? Great, okay. Does anybody know the magazine? Okay, yeah, lots of people, great, okay. Yeah, so, oops. Shit. Okay, yeah, so when I was in third grade, I saw this article. I saw this picture and I was fascinated by it. And yeah, it really got stuck in my head. So a couple of years, well, decades later actually, I decided to do some reverse engineering. And I loved it. I had so much fun with it. And yeah, so maybe I can turn some of you guys into reverse engineers themselves. Who knows? Okay, so, but first, let's start off with a little bit of history. So the company Magnetic Scrolls, the one I was fascinated about, this one existed between 1984 and 1992. And yeah, it is important to note that this company never went bankrupt. They just went out of business, and their assets, they were properly sold. Okay, oh shit, I need a second. I just lost something here. I'm really sorry. Okay, so yes, so okay, let me, where was it? Okay, yeah, let's start, okay, a little bit of history. So they existed between 1984 and 1992. In the end, they were sold. And yeah, they existed during the, I would like to say, heyday of text adventures. They produced 7 of them, which was not that much if you compare it to the other company. You know what company I'm talking about? The American one? Sierra, okay. I was actually talking about Infocom. Yeah. They produced more known games such as Sword, but this one was a British company. And yeah, they were famous for not only for their British humor, they were also famous for their for the beautiful graphics that you've seen in the first in this article before. Okay, but it did not start off with graphics. Their very first game, The Pawn, that was meant as a showcase for the new Spectrum QL computer by Sir Clive Sinclair. It was meant to really show how great this new platform was. I mean, it was 1985. And by that time, about a dozen 8-bit home computer platforms were fighting for dominance on the market. And this one came out, and it had a 68,000 processor, which was capable of if I'm not mistaken, 32-bit calculations. That was a lot. And to really show this, what they did was they wanted to have a game which had a very powerful parser. And this parser was so powerful that it was even able to understand complicated sentences like this one here. Plant the pot plant in the plant pot with a trowel. And everybody, yeah, when you read about magnetic scrolls, you always come across this sentence. And yeah, in the media, everybody was like, oh my God, magic. Or, oh my God, artificial intelligence. Yeah, and yeah, well, it was not that. I will tell you in the next chapter. Anyways, but magnetic scrolls had a slight problem because the Spectrum QL, that was not selling very well. The other platforms were a little bit better. And but yeah, everything was written in this 68,000 assembler. And yeah, how were they able to get their sales up, to get to the other platforms? And yeah, their solution was virtual machines. All the games were still written in this 68,000 assembler. They are still being written in this assembler. They are still being written in this assembler. All the puzzles, all the all the stories in there. And this 68,000 assembler was then simply emulated on all the other platforms, which had the great advantage. When a new platform came out, they did not have to rewrite their whole game, all the puzzles, all the story in this new assembler. All they had to do was they had to port this emulator. And yeah, so the disadvantage of that one was, of course, when you write a game and you needed at some point access to the hardware, like showing a picture, drawing some text, or have some calculations which take way too long if they are just emulated. Then they implemented some callbacks in the form of line 8 traps. So the game, in the end, that was running in two domains. So one in the 68,000 assembler, one on the host machine. And yeah, that was their basic architecture that you can see here on the top right. And in 1992, Niklas Carlsen came up with his own implementation of the engine. That was actually the first one being written in C, if I'm not mistaken. He called it Magnetic. And to make it easier for users to play those games, he came up with this with those two new file formats, .mac and .gfx. And yeah, like any good binary file, it contained some sections. So the code section was used to initialize the RAM. That was where the actual game was in. And then there was also there were also those two string sections, string 1 and string 2. And yeah, the dictionary, which was actually the key to understanding the parser. So a couple of years later, 2021, I wrote DMagnetic, my very own parser. I also started off with those Mac and .gfx files. And in 2021, during the pandemic, I opened up this website, magneticscrolls.net, and there you can play all the old games from 9 different platforms online over SSH. Yeah, we have a demonstration downstairs where you can play old text games over Telnet. Minus SSH. I'm sorry. Okay, so yeah, so I promised you data structures. So let's start off with the dict section that was in the Mac file. That is actually the easiest one. So can you read it? No, of course you cannot read it. I'm sorry about that. So when you do some reverse engineering, then the most important tool you have, that is a hex editor. And yeah, if you would have been able to read it, I'm sorry, it's slightly out of focus. Or can you read it? Can you read it? Okay, great. There are almost some words on the right-hand side. And yeah, so the words always seem to stop right before the last letter. So there's then there's a, there's some, and whatever. And the reason because it looks like that on the right-hand side is because well, what they did was to separate the words. They set the highest bit of the byte, and yeah, that was separating the word. And every once in a while, you see there's a code in there, 82. I highlighted those codes. And what this 82 does, it signifies the end of what they called a bank. And yeah, so when you can think of it as a CSV file. So yeah, lots of columns, lots of lines. In each column, you can find one word, and in each line is a bank. So pretty simple format, right? And what this dict section contained, those were all the words that the parser was able to understand. So yeah, I've just given you the size of those sections here for all the games, and you can see that the parser started off relatively rudimentary with the dict, with the pawn. And then their last game, Wonderland, that was capable of yeah, that had a dict section of 12,000 words. So imagine how many words that one was able to understand. So once again, the larger the dict section, the more words the game was able to understand. Okay, and to give you an idea of how this parser worked, I took the liberty, I decoded the banks 4, 5, and 6, and 21 for you. And when you look at those banks, and you remember this the sentence, plant the pot plant in the plant pot with a trowel, then you'll notice that yeah, you can find the word plant 3 times in this whole dict section. One in a line with lots of verbs, then in a line with lots of adjectives, and then in a line with lots of nouns. And yeah, there's also the pot, which is also an adjective and a noun. And yeah, so when you look at it, you should get an idea. I don't want to fully ruin the magic for you guys. So yeah, I'll stop right here. Okay, so that was the dict section. The next interesting dict section was the text section, or sorry, the string 1 and the string 2 sections. So the games I'm talking about are Textadventures, and in those Textadventures there were lots of text in there. And what they did was they packed those text. So in the end, the text was only 40% as large as it was before. Does anybody know why they did do it? Why did they do that?
Limited memory size. So.
Limited memory size. Very good. Thank you very much. Yes. Okay, great. Yep, so, and the technique they always used for that one, those were Huffman trees. Huffman trees, that was something actually from the 50s. And Huffman trees are entropy, yeah, that's a form of entropy coding. What you can see here on the right-hand side, I think I have to get up now. This is actually the original tree from the pawn. And yeah, my girlfriend told me that those letters are way too small. Nobody will be able to read it. I'm sorry, she was right, as always. Yeah, so what you can see here is so those green bubbles here, those were the terminal symbols, and yeah, some terminal symbols are much higher up, some terminal symbols are much lower down. And what you need to decode those trees, this is a bit stream. And yeah, so when you have a bit stream, the bit stream would then tell you how to traverse this tree. 0 would tell you, okay, go to the left. 1 would tell you, go to the right. And yeah, there are letters which I used here as an example are the letters E, which is way up there on the top right next to the 1. It was possible to decode this letter E with just 3 bits then instead of the full 8. But for the letter V, you needed more bits, just yeah, 16. But in the end, it evened itself out, so they ended up with just 40% roughly for the whole text. And again, this was because memory was limited. Okay, so yeah, and what I can also tell you, I think here you can see it a little bit better. Yes, there's on the top right, you can see the E in the green bubble, and I can tell you, magnetic scrolls loved their Huffman trees. I found them everywhere, and yeah, so whenever I did reverse engineering and encountered one of those trees, then yeah, I also encountered some bit streams. And yeah, my questions were then always the same. How, where are the ones stored? Where are the zeros stored? How was the terminal symbol encoded? And in particular, sometimes I also had to think about, okay, so a terminal symbol is only 6 bits wide. How would I be able to turn this one into a full 8-bit byte? So that was a question which I asked myself a lot when I came to the graphics, which is what I'm going to talk about tomorrow. Okay, so, but after a while, I was able to really understand this, those Huffman trees. And yeah, so, maybe you guys have seen Matrix, right? Okay, then you know, okay, I don't see the matrix anymore. I only see blondes, brunettes, redheads. And after a while, I really got to the point that I was really able to spot a Huffman tree just by looking at the hex code. Seriously. Yeah, can you guys spot a Huffman tree in here by any chance? Nope. Okay, can you spot the index? An index? Okay, so yeah, for me, after a while, I really got used to it, and then I realized that that those numbers that you can see on the top, well, they are increasing, and then there's a gap, and then there's the next number, then there's another gap, and then there's another number gap, and whatever. And yeah, so as it turns out, the numbers which are here in the top. On the top, those are actually links to other branches within the tree, and whenever they're and the other numbers or the other bytes, which I did not highlight here, when you look at them closely, you will notice that they always have the highest bit set, and those were the terminal symbols. And yeah, so. Okay, and so the example which I wanted to show you a couple of slides before, those two letters E and V, they are here in the red circles that you can see here. And as for the index that I found in there, I noticed that those numbers here at the bottom, those are 16-bit values. And they are also increasing. Can you see them? So it starts off here with 0, 0, then 0, 5a, 0, 9f, and so on. Can you see it now? Okay, so yeah, and I was able to spot an index whenever I noticed that every second byte was increasing. Okay, so now you know all my metric skills. I hope I'm not running into an agent. Okay, great. And yeah, now that we know how those data structures look like, the question was, how does it actually work from a programmer's perspective? So as I said before, all the games were written in 68,000 assembler. You guys remember? Okay, so and yeah, whenever they wanted to do some callbacks to the hardware, what they included was a special opcode, this line A trap. And yeah, so and yeah, I've given an example here. I wrote the value 1 into one of the registers, and then I inserted an opcode A0F8. Is anybody here proficient with 68,000 assembler? Nobody? Okay. So I can tell you that this opcode does not exist on this machine. So the yeah, then the emulator, of course, would know. Okay, I would have to take over. And what it did was it opened up those two sections, string 1 and string 2. It took from the index. In the index, it's yeah, there was the pointer towards the beginning of the bit stream, And the bit stream, that was what was stored in stream 1. Took the bit stream, 0, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, and whatever. Started to decode that one. And then this text would come out. You are on the gravel path. To the east is a vast grassy wilderness, and the dying forest is westward. The path also continues south. So, when you look at those sentences, or when you look at the output of what I decoded, what do you see? No low caps, right? What else? No blanks, yeah, no spaces after the dots and the commas. And yeah, of course, this was again to preserve some memory. Okay, so and yeah, when the games got bigger, this string 2 section, it had to evolve. What they had to or what they did when they got more and more text was they decided, okay, let's split up the string 1 section. And to preserve memory, and I don't know if they would have made it backwards compatible, I don't know. And they reused this very first index, index 0. Because, yeah, you can imagine that this index was always explicitly pointing towards the beginning of the string 1 section. And yeah, you can also make this one implicitly, and yeah, you would have saved 16-bit by that. Yeah, so they used this first index to really point to another index in the list. So whenever the emulator had to print out a text which was larger than this first entry, then it would show something from the second part of this string 1 section. Okay, so, and the next slide, that one really shows you why I love reverse engineering. Because every once in a while you find sentences like this here when you start decoding all the old data by yourself. This is first of Ken's test NPC messages. So obviously, this is a sentence I would have never seen if I would just have played the game. But yeah, it was still in there waiting for me to find, so I consider this one my treasure. Okay, so I've told you now a lot about those sections, but I have not really told you where they were actually coming from. Yeah, so, and my process, okay, yeah, and yeah, so I always wanted to play the original games. And nowadays, when you want to play the original games, you can find emulator images on archive.org, on IF-archive, and wherever, all over the internet. I think what was his name? Peter. He called it abandonware. And yeah, I wanted to be able to read the games from those emulator images in the end. And yeah, so and this is what I understood. Or yeah, I do understand them first, and this is what I understood. So those sections, they were stored somewhere. They were stored somewhere on those in these images. Sometimes the images they were real disk images with a real file system. So then those sections were simply files in there. And sometimes those files were packed. Sometimes they were encrypted. And yeah. And yeah, so when they were encrypted because of copyright protection, whatever, I really had to be able to decrypt them. And by no means I was no expert on copyright protection in the 80s, so nope, I wasn't able to do this. So, but I found a way how to do it, and I'm giving you an example on how how it could be done for the C64. But to be honest, I didn't do it for this machine. because Magnetic already did that. They already cracked those encryption for me, and I just had to copy over their C code or read it and understand it. I didn't copy anything from them. So. And yeah, but I did similar things on other platforms. So I always so again, my goal was I want to start off with an image emulator image file, and I wanted to be able to create those .mac and those .gfx files. So my process was always that I took out an open source emulator and I changed the source code a little bit. So I changed the source code in a way that I would be able to track all the memory writes. And yeah, so when you look at the C code over there, I'm just dumping the address and the value which was written. And I really thought long and hard about how to visualize it for you guys. And yeah, so this was my first attempt. So what you see here, those are 256 by 256 pixels. This animation here, this one is representing all of the addressable C64 memory. But if I just color it black for 0 and white for FF, you can only see, okay, so something is happening. You can get an idea in which order everything is happening, but you do not really know what the data is that you're seeing here. So yeah, but when I start coloring everything here in yellow, when it was a byte sequence that I was able to find the same way on the emulator images, then you get yeah, then you can see a little bit more. And when I started comparing everything with the .mac file I got from another platform, and then I noticed, oh my God, there's also lots of code in here that I already understand. So yeah. Okay, so when I animate this process again, like this, you have a better idea of what is really going on. So what you're seeing here now is when I started when the pawn already started, or no, when it was loading. I'm sorry, when it was loading, and when it was then loading the very first picture. And yeah, you can see here there are some sectors from the disk being read, and all of a sudden the code section from the other platforms, that one appeared magically. I don't know. And yeah, there's a section down there somewhere just below the middle, where you can see, okay, it started off as a section from the emulator image, and then becomes something from the .mac file. So yeah, when I zoom in that one, you can really see what is going on. So again, each row here has each line represents 256 bytes. So this whole square here contains 1 kilobyte. And yeah, you can see there was some data being loaded from the floppy, and then something happened, and then it became from left to right. It becomes the code section. And yeah, so then I know where it happened. I really saw what happened. No, I did not see what happened, but I see when it happened and where it happened. So then I was able to add some more code to the emulator, really look at the instructions that were being produced, and then from that I learned that this little algorithm you see here on the left, that was the one which was being performed. Okay, so yeah, I found the exact same algorithm. I called it here something with a pivot on not only on the C64. I found it also on the Atari and Apple II releases. And yeah, the Atari, the Amstrad CPC, they did something slightly different. They used PRBS, so pseudo-random bit sequence. And what they did was just create one element of the PRBS after the other, and XORed that one with the bytes it read from the emulator image, or from the floppy. Sorry. Okay, so that's all. That's almost it. So to sum up, I told you a little bit about the history of magnetic scrolls. I destroyed the magic of the parser. I showed you how to pack some text 80 style and how to find some treasure in there. I told you how to read emulator files and how I was able to crack some code. I put some links here on the right-hand side. Yeah, I will come back to this slide later, but I would like to close with one last thing. So yeah, when I was working with the Spectrum releases of the game, this is what I found. I opened up the disk file with the hex editor, and I saw Fatman and Dobbin strike again. Don't waste your time trying to find out how it works. It's far too clever for someone like you to understand. Okay, so of course I was able to understand it after a while. So I got in contact with Hugh Steers. He was the founder of Magnetic Scrolls. And I asked him, Hugh, can you send those guys this picture, please? So yeah, he sent this picture over to Richard, and he told with the line, "Richard, consider yourself hacked." And Richard, aka Fatman's reply was, "Okay, I got hacked." Great, thank you for your time.
So you mentioned this scrambling algorithm.
Yes.
What was exactly the goal of this? Is it a kind of copyright protection or obfuscation, or I just didn't get the deeper goal of this algorithm?
Yeah, it was actually just security by obscurity. If you would have put in the raw text or the raw source code, everybody would have been able to read it. Everybody would have noticed, oh my God, this is 68K assembler. And it would have also been much easier to really remove any copyright protections.
Okay.
So if you ever play the original games, then every once in a while there's this question, okay, please enter this line from that page or this word from that line on that page in the manual. What is it? Otherwise, you're not allowed to play anymore. And
Right.
that was in there.
Okay. Okay. And the second question, if I may. So you said there's this virtual machine running 68,000 code. How did you debug that one? Did you have a special debugger in order to do that, or because it's embedded in the actual machine, so it's difficult? Or?
Okay, yeah, like I said, I was not the first one to really do this. It was Nicholas Carlson, and his interpreter, he called it magnetic. I was not that creative on the name. I just called mine demagnetic. Whatever. So to really debug those, that actually took a long time. I had to run those two together.
Okay.
So I really started looking at how do those the values in the register, how do they behave, how does my memory look like, and everything when I run the program. I noticed there were some bugs in his implementation. Unfortunately, to be able to follow with that process, I had to replicate those bugs. But in the end, it worked out.
Okay, great, thanks.
Oh, and also the 68K followed also the original specification of the actual 68K.
So since you basically make them free to play at the moment, and you said the original company didn't go bankrupt, but it was sold. Do you know who owns the rights to those games now?
Well, I do know Hugh Steers. he really loves my stuff, and he actually owns this domain magneticsquirrels.net now.
Oh, nice.
And
Okay.
he has no problems with me allowing other people to play the games. Well, you cannot download the games from my website, so even if there would be some legal issues, that's not my fault.
Okay, perfect. So that's basically the way it should be all the time, right?
Yes. Yes.
Okay.
So if you want to play the games, or if you want to download them, you can find them on archive.org or ifarchive.org. And yeah, all I'm doing is I'm offering another interpreter of the game, another virtual machine. Oh, not the machine. You know what I mean. Great. So thanks again for your time, guys.